Hi everyone, this is your old anatomy professor Becky, here with another episode helping you review acid-base balance, or pH. pH was your favorite. So let's start by reminding ourselves what we're dealing with pH. We're looking at the concentration of hydrogen ions. This time we're interested in the blood. Now remember, neutral is a pH of around 7. Blood pH should be close to 7.4, technically between 7.35 and 7.45. This is a really interesting example of homeostasis where it's not a set, right, 7.4, but it is a very narrow range that your blood pH needs to be maintained in or you get really sick, right? You drop down to about 6.9, that doesn't sound so low, that'll kill you. Okay, so again, recalling that low pH numbers, right, as we get increasingly lower, that means more hydrogen. This is an inverse scale. So when you hear about someone who has acidosis, that means their blood pH has fallen below 7.35. On the opposite end of the scale, where we start to see higher pH numbers, this indicates a lack of hydrogen, a low level of hydrogen. This is also problematic, right? A lot of us think about acid as being bad, but bases are bad as well. And so again, anything a pH above 7.45 is going to be considered alkalosis. You will see acid-base balance become important in a lot of different situations. Okay, so in order to maintain that really narrow blood pH, we have really three different things that the body's going to use. Our buffers, and here we're looking at a few different examples of buffers, but basically what we have is either a weak acid willing to donate a hydrogen or a weak base, something willing to accept some hydrogen. Now, one of the really cool examples of buffers are the proteins. So things like hemoglobin or maybe a plasma protein like albumin, but really any amino acid can act as a buffer. And here's what it looks like. Here's your prototypical amino acid. On one end, there's a hydrogen kind of hanging off the side. And so if the pH rises, if you start to become slightly alkaline, what amino acids will do is they'll act as a weak acid. They'll go ahead and donate that hydrogen to make sure that you maintain a neutral pH. But amino acids can do the opposite as well. The amine group here, this nitrogen containing group, notice what happens if the pH falls. If you start to become acidic, that amine group is actually willing to take on another hydrogen, take one for the team, and make sure that that blood pH remains neutral. Okay, so those are our buffers. We also are going to see that the lung and the kidney are the two organs that really come into play here. So here we're looking at the lung. The lung is super important and it works alongside a buffer. So here is the carbonic acid bicarbonate buffer system. You guys loved this equation. Remember, the carbon dioxide plus water can make carbonic acid, which then can dissociate, fall apart into hydrogen and bicarbonate. See, you remember this one? You guys love this one. Okay, so here's how it works, right? The lung, if you start breathing off lots of CO2, you can actually kind of pull hydrogen out of the blood, right, by putting it into carbonic acid and then breathing it out the lung as CO2. But you can do the opposite. If you slow the respiratory rate, if you hold on to CO2, that CO2 can join the water and will push the equation this way and actually release acid into the blood. Okay, so the lung is going to be super important in maintaining blood pH. And it does that through CO2. And this is always confusing to people. This is super key to understand. And maybe a simpler way to think about this, higher carbon dioxide levels mean a lower pH, right? More CO2 pushes this equation to the right. You produce more hydrogen, and that lowers the pH. So this is an inverse relationship. High partial pressure of carbon dioxide, low pH. Low partial pressure of carbon dioxide, higher pH or more alkaline pH. Okay? So the lung and its ability to expel CO2 is going to be super important. The other organ is the kidney. Now, without getting too crazy into all of this, notice here is your equation again. And on this side, we see a situation where the kidney is actually excreting hydrogen. It's putting it out here into what will become the urine and expelling it from the body. Okay. On this side, this is the same equation, it's just kind of turned sideways. We see that the kidney can also go ahead and bring hydrogen into the blood, right, to lower the pH, and secrete or excrete bicarbonate in the urine. So the kidney kind of gets to choose, do I hold on to bicarbonate and excrete hydrogen, or do I hold on to hydrogen and excrete bicarbonate? And so the kidney is really useful in this process as well. And so here we see it kind of all together. So this is what the body does in response to acidosis. So a falling blood pH, right? We've got too much hydrogen here at the beginning. We've got our buffer systems that can try to absorb hydrogen. So they're, maybe it's attaching to hemoglobin or albumin, something like that. We also see that the lung can essentially expel that acid in the form of CO2. And here we see the kidney go ahead and secrete the hydrogen. So all three of these things can actually work together. The opposite happens if the blood pH climbs and someone is becoming alkalotic. So we're losing hydrogen for some reason. Maybe lots of vomiting, right? We keep losing hydrogen. And so here we're going to see buffer systems giving up some hydrogen, right? Trying to neutralize pH. We can see that the lungs, you might actually decrease the respiratory rate to try to push our equation here into making more hydrogen. That would fix our problem. And then here we see the kidney actually making hydrogen and sending it to the blood while secreting bicarbonate. So these three things, buffers, the lung, and the kidney, are going to work together. I included this. This might be helpful as you're looking at things like alkalosis and acidosis. A nice little flow chart. Notice on this side, acidosis is a condition where the pH has fallen below 7.35. Alkalosis, if the pH is below 7.45. And then from there on down, you're looking at, well, is it metabolic in origin or respiratory in origin? I won't go into that. That's where you're heading in this class, but I hope that little review of pH helped.